Hey dear, welcome to another video on our PyTorch playlist for artificial intelligence. Hope you guys are doing well. Today, we are going deep dive in transformers. If you have stick with us on our last video, you may have watched how important is transformers while dealing with large language models, and how does it get imply on predicting the next word. Today, we will build one transformer model from scratch and use it on our own datasets. Before diving in, let's understand what transformers are. Transformers were first developed to solve the problem of sequence transduction or neural machine translation, which means they are meant to solve any task that transforms an input sequence to an output sequence. This is why they are called transformers. What are transformer models? A transformer model is a neural network that learns the context of sequential data and generates new data out of it. To put it simply, a transformer is a type of artificial intelligence model that learns to understand and generate human-like text by analyzing patterns in large amounts of text data. Transformers are a current state-of-the-art NLP model and are considered the evolution of the encoder-decoder architecture. However, while the encoder-decoder architecture relies mainly on recurrent neural networks, RNNs, to extract sequential information, transformers completely lack this recurrency. So, how do they do it? They are specifically designed to comprehend context and meaning by analyzing the relationship between different elements, and they rely almost entirely on a mathematical technique called attention to do so. Transformer architecture, originally devised for sequence transduction or neural machine translation, transformers excel in converting input sequences into output sequences. It is the first transduction model relying entirely on self-attention to compute representations of its input and output, without using sequence-aligned RNNs or convolution. The main core characteristic of the transformers architecture is that they maintain the encoder-decoder model. However, both the encoder and the decoder are actually a stack with multiple layers, same number for each. All encoders present the same structure, and the input gets into each of them and is passed to the next one. All decoders present the same structure as well and get the input from the last encoder and the previous decoder. The original architecture consisted of 6 encoders and 6 decoders, but we can replicate as many layers as we want. So let's assume n layers of each. So now that we have a generic idea of the overall transformer architecture, let's focus on how it works. So let's get coding.
So let's get into coding. Things will make sense accordingly. So before getting into main points, let's import the packages. In case your system lacks the packages, make sure to install it using pip command. Let's begin. You will find the repo link in the description. Make sure to follow along. Import O's. Import requests. Import pandas as p. Import matplotlib.pyplot as pult. Import math. Import tick token. Dake. Import torch. Import torch.nm as in. Next, let's get into hyperparameters. Before diving into code section, what are hyperparameters actually? In machine learning, a hyperparameter is a parameter that can be set in order to define any configurable part of a model's learning process. Hyperparameters can be classified as either model hyperparameters, such as the topology and size of a neural network, or algorithm hyperparameters, such as the learning rate and the batch size of an optimizer. These are named hyperparameters in contrast to parameters, which are characteristics that the model learns from the data. The time required to train and test a model can depend upon the choice of its hyperparameters. A hyperparameter is usually of continuous or integer type, leading to mixed-type optimization problems. The existence of some hyperparameters is conditional upon the value of others, e.g., the size of each hidden layer in a neural network can be conditional upon the number of layers. Now let's see into use case. We are setting the batch size, context length, model, dropout, numheads, max underscore iterators, device, and other for hyperparameter setting. Hyperparameters, unts, to batch underscore size 4, how many batches per training step. Context underscore length, 16, length of the token chunk each batch. D underscore model 64, the vector size of the token embeddings. num underscore layers 8 number of transformer blocks. Num underscore heads 4 number of heads and multi-head attention. Learning underscore rate 1e minus 3 0.001. Dropout 0.1 dropout rate. Max underscore iters 500 total of training iterations. Eval underscore interval 50 how often to evaluate the model. Eval underscore iters 20 how many iterations to average the loss over when evaluating the model. Device QDA if torch.QDA is underscore available, else Q instead of using the Q will use the GPU if it's available. Torch underscore seed 1337. Torch.manual underscore seed, torch underscore seed. Now let's download the sample file. You'll find the link in the description. Just follow along. Download a sample text file. If not os.path.exists, data/text.txt. rolltaps:/github.com/saruji001/blob/transformers/blob/main/text.txt. With open text.text.w as f. f.write request.get url.text. With open data/text.txt encoding f8 as f. Text f.read. Now we are going to use tick token to tokenize the source text. We will tokenize the text in maximum token value. Encoding tick token.get underscore encoding call 100k underscore base call 100 key underscore base is a standard method for encoding. Tokenized underscore text encoding dot encode text. Tokenized underscore text torch.tensor tokenized underscore text type torch.long device convert tokens into a tensor. Max underscore token underscore value tokenized underscore text dot max dot item the maximum index value in our vocabulary. Print f tokenized text size len tokenized underscore text. Print f the maximum value in the tokenized text is max underscore token underscore value. Run the cell, you will find the text size. Now we are getting into illustration purpose. We will encode the text and decode them further in this kernel. If you are not very comfortable with how encoding and decoding work, watch our previous video where we have tokenized the text and covered how things go on. Let's get coding. Illustration purpose. Print encoding.encode Chapter 1 Building Report and Capturing. Print encoding.decode 26,072 220 1625 17,283 23,097 403 323 17,013 1,711. Report is tokenized as 2 tokens, wrap 230-297 and port 403. Print encoding.decode 627 1,383 88,861 279 1989 315 25,607 16,940 65,931 323 32,097 11 584 26,458 13,520 449. The characters are nothing, but it denotes the words in our text file. You can experiment on your own by putting different numbers. It will generate different text. And now let's split and train and validate the data. Split train and validation. Split underscore IDEX int, len tokenized underscore text, 0.9. Train underscore data tokenized underscore text, split underscore IDEX. Val underscore data tokenized underscore text, split underscore IDEX. Now let's prepare the data training batch. Prepare data for training batch. Data train underscore data. It's torch.random, low 0, high len, data context underscore length, size batch underscore size. X underscore batch torch.stack data, xidex context underscore length for ids and ids. I underscore batch torch.stack data, edx1 ids context underscore length 1 for ids and ix. Print x underscore batch dot shape, x underscore batch dot shape. Moving on to next kernel. Illustration purpose. P.set underscore option display.expand underscore frame underscore reper. False. Print. Our batch's MPD data frame, x underscore batch dot data dot detach dot q dot numpy. Next, we are going to define the token embedding lookup table. Define token embedding lookup table. Token underscore embedding underscore lookup underscore table nn dot embedding max underscore token underscore value 1d underscore model. Print token embedding lookup table token underscore embedding underscore lookup underscore table. Next, we are going to embed the x and y variables. Get x and y embedding. X underscore batch underscore embedding token underscore embedding underscore lookup underscore table x underscore batch dot data 41664 batch underscore size context underscore length d underscore model e underscore batch underscore embedding token underscore embedding underscore lookup underscore table y underscore batch dot data x underscore batch underscore embedding dot shape y underscore batch underscore embedding dot shape. And now we are going to deal with encoding lookup table. We will first encode the lookup table in context length model as a parameter considering div term position underscore encoding. Follow along so that things can make sense. Define position encoding lookup table. Position underscore encoding underscore lookup underscore table torch dot zeros context underscore length d underscore model. Position torch dot arrange 0 context underscore length d type torch dot float dot unsqueeze 1. Div underscore term torch dot exp torch dot arrange 0 d underscore model 2 dot float dash math dot log 10,000.0 d underscore model. Position underscore encoding underscore lookup underscore table 02 torch dot sin position div underscore term. Position underscore encoding underscore lookup underscore table 12 torch dot cause position div underscore term. Position underscore encoding underscore lookup underscore table position underscore encoding underscore lookup underscore table dot unsqueeze 0 dot expand batch underscore size -1 add batch dimension. Print. Position encoding lookup table position underscore encoding underscore lookup underscore table dot shape 41664 batch underscore size context underscore length d underscore model. dd.data frame, position underscore encoding underscore lookup underscore table, 0.detach.chew.numpy. This will showcase the characters of our data in the format of arrays and table. You can look below. Now, let's visualize the positional encoding. Taking positional index and encoding index. Illustration purpose only. Def visualize underscore p. Pult.imshow p aspect auto. Pult.title positional encoding. Pult.xlabel encoding dimension. Pult.ulabel position index. Pult.colorbar. Pult.show position underscore encoding underscore lookup underscore table 2 underscore net position underscore encoding underscore lookup underscore table 0.crew.numpy visualize underscore p position underscore encoding underscore lookup underscore table 2 underscore net. Let's put some neural network in our transformers model. Getting into our next kernel. Add positional encoding into the input embedding vector. Input underscore embedding underscore x underscore batch underscore embedding score encoding underscore lookup underscore table 41664 batch underscore size context underscore length d underscore model. Input underscore embedding underscore y underscore batch underscore embedding position underscore encoding underscore lookup underscore table td.dataframe input underscore embedding underscore x0 dot detach dot q dot numpy. This will showcase the characters of our data in the format of arrays and table. You can look below. Next, we are going to deal with multi-headed function. Prepare query key value for multi-head attention. X input underscore embedding underscore x. Query key value x4 1664 batch underscore size context underscore length d underscore model. Query dot shape. In our next kernel, we are going to define query key value weight matrices. WQNN.linear D underscore model, D underscore model. WKN.linear D underscore model, D underscore model. WBNN.linear D underscore model, D underscore model. QWQ query 4, 1664. QQ.view batch underscore size, -1, num underscore heads, D underscore model num underscore heads 4, 16, 4, 16. KWK key 4, 16, 64. KK.view batch underscore size, -1, num underscore heads, D underscore model num underscore heads 4, 16, 4, 16. VWV value 4, 16, 64. VV.view batch underscore size, -1, num underscore heads, D underscore model num underscore heads 4, 16, 4, 16. Print torch.round q0 100 100. QQQ.detach.cpu.numpy. For QS in QQ. For QSS in QS. Print pd.dataframe QSS. Print q.shape 4, 16, 4, 16 batch underscore size context underscore length num underscore heads head underscore size. Now we're going to transpose q, k, v from batch underscore size, context underscore length, num underscore heads, head underscore size to batch underscore size, num underscore heads, context underscore length, head underscore size. The reason is that treat each batch with num underscore heads as its first dimension. QQ.transpose 1, 2, 4, 4, 16, 16. KK.transpose 1, 2, 4, 4, 16, 16. VV.transpose 1, 2, 4, 4, 16, 16. Now let's calculate the attention score. Attention underscore score torch.matmul q, k.transpose dash 2, -1 math.score td underscore model num underscore heads 4, 4, 16, 16. Illustration only. plt.m show attention underscore score 1, 1.detach.cpu.numpy, accent aspect auto. pt.title attention q at kplot attention in the first head of the first batch. plt.xlabel encoding.decode x underscore batch 0.tolist. plt.elabel encoding.decode x underscore batch 0.tolist. plt.colorbar pd.dataframe attention underscore score 00.detach.cpu.numpy. Next, we are going to apply mask attention scores. Attention underscore score attention underscore score dot masked underscore fill torch dot trio torch dot one's attention underscore score dot shape dash 2 diagonal 1 dot bool float enfe octi 4 16 16 batch underscore size num underscore heads context underscore length illustration only. plt.m show attention underscore score 1 1.detach.cpu.numpy accent aspect auto. plt.title attention q, k. plt.xlabel encoding.decode x underscore batch 0.tolist. plt.elabel encoding.decode x underscore batch 0.tolist, plt.colorbar, pd.dataframeAttention underscore score 00.detach.cpu.numpy. Next, we are going for softmax attention score. The softmax function is used to convert raw attention scores into a probability distribution in transformer models. This distribution helps the model understand the relative importance of words in a sequence, which can improve its performance in tasks like translation and generation. Let's get coding. Attention underscore score torch.softmax attention underscore score dim 1441616 batch underscore size num underscore heads context underscore length but pd.dataframeAttention underscore score 00.detach.cpu.numpy. Next, let's calculate the v-attention output. Print attention underscore score dot shape 16 batch underscore size num underscore heads context underscore length. Print v dot shape 16 batch underscore size num underscore heads context underscore length head underscore size. A torch.matmul attention underscore score v16 batch underscore size num underscore heads context underscore length head underscore size. Print a dot shape. Let's concatenate the attention output. Concatenate the attention output. A dot transpose 16 batch underscore size context underscore length num underscore heads head underscore size. A dot reshape batch underscore size -1 d underscore model 1664 batch underscore size context underscore length d underscore model. A dot shape. Let's now define the output weight matrix. Wo nn dot linear d underscore model d underscore model. Output wo of 64 batch underscore size context underscore length d underscore model. Print output dot shape. pd dot dataframe output 0.detach.cpu.numpy. Add residual connection. Output x. Next, add layer normalization. Add layer normalization. Layer underscore norm nn dot layer norm d underscore model. Output underscore layer norm output. Next, we are going to define our feed-forward neural network. Output nn dot linear d underscore model for output underscore layer norm. Output nn.relu output. Output nn.linear d underscore model for d underscore model output. Output torch.dropout output p dropout train true. Next, we are going to add residual and layer norm. Output underscore layer norm. Add layer normalization. Layer underscore norm nn.layer norm d underscore model. Output layer underscore norm output. Print output dot shape. After all the steps I have mentioned above, you have successfully completed the transformer block. Now, let's apply the final linear layer logit to get the logits. Logits nn.linear d underscore model max underscore token underscore value 1 output. ed.dataframe logits 0.detach.cpu.numpy. Get the probabilities. Torch.softmax usually used during inference. During training we use torch.nn.crossentropylos. Probabilities torch.softmax logits dim1. ed.dataframe probabilities 0.detach.cpu.numpy. Now we are getting into predicting the tokens. Let's see the predicted token and its original English word. Predicted underscore index torch.argmax logits 0.item. Encoding.decode predicted underscore index. You can change the logits parameter and it will showcase you different tokens accordingly. Let's see the original input sentence. Encoding.decode x underscore batch 0.tolist. You can change the parameter of the batch size. The prediction may show some problems as we are not training the transformer model, but anyhow, this is how transformer works in the realm of artificial intelligence. Now let's train a transformer model and check out how things work. First, we need to use the hyperparameter. Follow along with me, this script may be lengthy. Hyperparameters. Batch underscore size 4, how many batches per training step? Context underscore length 16 length of the token chunk each batch. D underscore model 64 the size of our model token embeddings. Num underscore blocks 8 number of transformer blocks. Num underscore heads 4 number of heads and multi-head attention. Learning underscore rate 1e minus 30.001. Dropout 0.1 dropout rate. Max underscore iters 500 total of training iterations. Change this to smaller number for testing. Eval underscore interval 50 how often to evaluate. Eval underscore iters 20 number of iterations to average for evaluation. Device CUDA if torch.CUDA is underscore available else CPU use GPU if it's available. Torch underscore seed 1337. Torch.manual underscore seed torch underscore seed. Load training data. If not os.path.exists text.txt. URL https://github.com/suruj00001/transformer/main/text.txt.txt with open data /text.txt w as f f.write request.getURL.text with open text.txt r encoding UTF-8 is f text f.read. Using tick token same as GPT-3 to tokenize the source text. Encoding tick token.get underscore encoding CL100K underscore base. Tokenized underscore text encoding.encode text. Max underscore token underscore value max tokenized underscore text 1 the maximum value of the tokenized numbers. Tokenized underscore text torch.tensor tokenized underscore text type torch.long device put tokenized text into tensor. Split train and validation. Split underscore idx int len tokenized underscore text 0.9. Train underscore data tokenized underscore text split underscore idx. Val underscore data tokenized underscore text split underscore idx. Define feed forward network. Class feed forward nn.module. Def underscore init underscore self. Super dot underscore init underscore self dot d underscore model self dot dropout self dot fnn dot sequential n dot linear in underscore features self dot d underscore model out underscore features self dot d underscore model 4 nn dot relu nn dot linear in underscore features self dot d underscore model 4 out underscore features self dot d underscore model nn dot dropout dropout. Def forward self x returns self dot fnx. Define scale dot product attention. Class attention nn dot module. Def underscore underscore init underscore underscore self head underscore size int. Super dot underscore underscore init underscore underscore underscore. Self dot d underscore model. Self dot head underscore size self dot context underscore length. Self dot dropout. Self dot key underscore layer nn dot linear in underscore features self dot d underscore model out underscore features self dot head underscore size bias false. Self dot query underscore layer nn dot linear in underscore features self dot d underscore model out underscore features self dot head underscore size bias false. Self dot value underscore layer nn dot linear in underscore features self dot d underscore model out underscore features self dot head underscore size bias false. Self dot register underscore buffer trill torch dot one self dot context underscore length self dot context underscore length lower triangular mask. Self dot dropout underscore layer nn dot dropout self dot dropout. Def forward self x. btcx dot shape batch size time steps current context underscore length channels dimensions. Assert t self dot context underscore length. Assert c self dot d underscore model. U self dot query underscore layer x. K self dot key underscore layer x. V self dot value underscore layer x. Scale dot product attention q at kt sqrt underscore k. Weights q at k dot transpose dash 2 minus 1.0 math dot sqrt got size dash 1. Apply masked attention. Weights dot masked underscore fill self dot trill colon t0 float in f. Weights f dot softmax input weights dim 1. Weights self dot dropout underscore layer weights. Apply dot product attention weights at v. Out weights at v. Return out. Now let's get into multi-headed attention. Like having a team of specialists instead of a single worker, multi-head attention utilizes multiple attention heads in parallel. Each head learns to focus on different aspects of the input. Diverse perspectives, one head might excel at capturing long-range dependencies in a sentence, while another specializes in understanding word order, and another tackles nuanced meanings. Enhanced understanding by merging the knowledge from different heads, the transformer develops a multidimensional, rich representation of the input text. This is crucial for tackling the complexities of natural language. Class multi-head attention nn dot module. Def underscore underscore init underscore underscore self head underscore size int. Super dot underscore underscore init underscore underscore. Self dot num underscore heads num underscore heads. Self dot head underscore size head underscore size. Self dot d underscore model d underscore model. Self dot context underscore length context underscore length. Self dot dropout dropout. Self dot heads nn dot modulist attention head underscore size self dot head underscore size for underscore in range self dot num underscore heads. Self dot projection underscore layer nn dot linear in underscore features self dot d underscore model out underscore features self dot d underscore model. Self dot dropout underscore layer nn dot dropout dropout. Def forward self x. Out torch dot cat hx for h in self dot heads dim 1. Out self dot projection underscore layer out. Out self dot dropout underscore layer out. Return out. Class transformer block nn dot module. Def underscore underscore init underscore underscore self num underscore heads int. Super dot underscore underscore init underscore underscore underscore. Self dot d underscore model d underscore model. Self dot context underscore length. Self dot head underscore size d underscore model num underscore heads head size should be divisible by d underscore model. self.num underscore heads num underscore heads, self.dropout dropout, self.multi underscore head underscore attention underscore layer multi-head attention head underscore size self.head underscore size, self.feed underscore forward underscore layer feed forward, self.layer underscore norm underscore 1nn.layer norm normalized underscore shape self.d underscore model, self.layer underscore norm underscore 2nn.layer norm normalized underscore shape self.d underscore model, def forward self x. Note the order of the operations is different from the original transformer paper. The order here is layer norm multi-head attention layer norm feed forward, xx self.multi underscore head underscore attention underscore layer self.layer underscore norm underscore 1x residual connection, xx self.feed underscore forward underscore layer self.layer underscore norm underscore 2x residual connection, return x. Class transformer language model nn.module, def underscore underscore init underscore underscore self, super dot underscore underscore init underscore underscore, self.d underscore model d underscore model, self.context underscore length, self.num underscore heads, self.num underscore blocks, self.dropout, self.max underscore token underscore value, setup token embedding lookup table, self.token underscore embedding underscore lookup underscore table nn.embedding num underscore embedding self.max underscore token underscore value 1 embedding underscore dim self.d underscore model. Run all the transformer blocks. Different from original paper, here we add a final layer norm after all the blocks. Self.transformer underscore blocks nn.sequential. Transformer block num underscore heads self.num underscore heads for underscore and range self.num underscore blocks. nn.layer norm self.d underscore model. Self.language underscore model underscore out underscore linear underscore layer nn.linear in underscore features self.d underscore model out underscore features self.max underscore token underscore value. Def forward self idx targets none. B tidx.shape. Setup position embedding lookup table. Following the same approach as the original transformer paper sine and cosine functions. Position underscore encoding underscore lookup underscore table torch.0 self.context underscore length self.d underscore model. Position torch.arrange 0 self.context underscore length dtype torch.float.unsqueeze 1. Div underscore term torch.xp torch.arrange 0 self.d underscore model 2.float-math.log 10,000.0 self.d underscore model. Position underscore encoding underscore lookup underscore table 02 torch.sin position div underscore term. Position underscore encoding underscore lookup underscore table 12 torch.cos position div underscore term. Change position underscore encoding underscore lookup underscore table from context underscore length d underscore model to t d underscore model. Position underscore embedding position underscore encoding underscore lookup underscore table t colon dot to device. X self dot token underscore embedding underscore lookup underscore table idx position underscore embedding. X self dot transformer underscore blocks x. The logits are the output values of our model before applying softmax. Logits self dot language underscore model underscore out underscore linear underscore layer x. If targets is not none. BTC logits dot shape. Logits underscore reshaped logits dot view BTC. Targets underscore reshaped targets dot view BT. Loss f dot cross underscore entropy input logits underscore reshaped targets underscore reshaped. Else when else. Loss none. Return logits loss. Def generate self idx max underscore new underscore tokens. IDX is B, T array of indices in the current context. For underscore in range max underscore new underscore tokens. Crop IDX to the max size of our positional embeddings table. IDX underscore crop IDX dash self.context underscore length. Get predictions. Logits loss self IDX underscore crop. Get the last time step from logits where the dimensions of the logits are BTC. Logits underscore last underscore time step logits -1. Apply softmax to get probabilities. Probs f dot softmax input logits underscore last underscore time step dim1. Sample from the probabilities distribution. IDX underscore next torch dot multinomial input probs num underscore samples 1. Append the sampled indexes IDX underscore next to IDX. IDX torch dot cat IDX IDX underscore next dim1. Return IDX. Initialize the model. Model transformer language model. Model dot to device. Get input embedding batch. Def get underscore batch split str. Data train underscore data if split train else val underscore data. IDX torch dot randint low 0 high len data context underscore length size batch underscore size. Xtorch dot stack data IDX colon IDX context underscore length for IDX in IDX dot to device. Ytorch dot stack data IDX1 IDX context underscore length 1 for IDX in IDXs dot to device. Return X, Y. Calculate loss. Add torch dot no underscore grad. Def estimate underscore loss. Out, count. Model.eval. For split and train, valid. Losses torch dot zeros eval underscore iders. For k and range eval underscore iders. X underscore batch, Y underscore batch get underscore batch split. Logits, loss model X underscore batch, Y underscore batch. Losses k loss dot item. Out split losses dot mean. Model dot train. Return out. Now we are going to optimize using Atom Optimizer. Use AtomMu Optimizer. Optimizer torch.optim.atommu params model.parameters lr learning underscore rate. Tract underscore losses list. For step and range max underscore iders. If step percent eval underscore iders 0 or step max underscore iders 1. Losses estimate underscore loss. Tract underscore losses dot append losses. Print step, training loss, round losses train dot item 3, validation loss. Round losses valid e dot item 3. XB, YB get underscore batch train. Logits, loss model XB, UIB. Optimizer dot 0 underscore grad set underscore to underscore none true. Loss dot backward. Optimizer dot step. Next, we are going to save the model in our directory. Save the model state dictionary. Torch.save model.state underscore dict model-akt.pt. Generate. Model.eval. Start to successfully handle objections related to competition. Start underscore IDs encoding.encode start. Xtorch.tensor start underscore IDs divetorch.long device none. Y model.generate X max underscore new underscore tokens 100. Print is shall print encoding.decode e0.tallest print trint af 2. You can take a different start text. Now let's run the kernel and let the model get trained. As you can see, it had successfully generated the text after the text we have taken from start from our test files. By uncertainty cues techniques potential impact a value easily but 3 into their customers and clears well. Your sales aligned to most alleviating have persuasive solid and established trust to interpreting these make issues a sharing the language ground. Follows. So, I guess you have got the basic idea, how transformer works. What are its use cases and how to leverage it in your work? Make sure that you can take any start text from the file we have taken. So that's it for today. Catch you up later.
So that's it for today. Hope you find the video useful. Make sure to follow our pages for staying ahead in the latest technology. All links are in the description. Till then, goodbye.